Welcome to CPUNK Explained. Nowadays, you often hear people say that this and that project is quantum proof or quantum secure, and you go like, yeah, well, I'm sure they are, but have you ever really thought about it? What makes them quantum proof? Is there any truth to those claims? If you're looking at an online service or let's say crypto project, first thing you look is the algorithms they're using. There are a handful of algorithms that are considered safe against quantum attacks, and the best of them are approved by NIST, a National Institute of Standards and Technology, as candidates for quantum secure algorithms. But now, as we're focusing on the quantum safety of CPUNK, we'll be diving into algorithms that are securing CPUNK's peer-to-peer messaging system. Kyber and its 1024-bit variation, which is used to encapsulate recipient keys. We're going to walk through the math problem behind it in a very simplified and understandable way. And I'm sure after watching this video, your head's gonna spin while you're trying to imagine how big numbers we're actually talking about. Enjoy. Kyber and dilithium are so-called lattice-based problems. They work the same way, but we're not only focusing now on the Kyber and its module learning with errors 1024-bit variation. Before we dive any deeper, I want you to understand what learning with errors mean. Actually, let's first create our initial lattice. So we start by drawing our origin 0 point. And here we go. Let's draw a couple of vectors. This is so-called easy basis, and it's representing our secret key. We call the lattice A, and these vectors go to coordinates read from 0.0 to x1 and y4, and the other one from 0.0 to x2 and y1. With these two vectors, we can draw an entire lattice. Just simply multiply, add, or subtract these from each other, and soon our lattice starts to form. It can go to infinity, but we'll stop here. Next, we need to define our bad basis, the public key. These vectors will be long and ugly, hence the name bad basis. They should define very skewed lattice, which looks pretty weird. But for the sake of clarity, we'll just keep them longish. The red one goes from origin to x8 and y4, and the green one from 0 point to 4.1. These vectors represent the public key. They define the lattice that everybody can see, and as you've probably noticed, they currently would form exactly the same lattice like our secret key. We'll stop here for a moment, as I need to explain you what learning with errors mean, and as that is the key component of Kyber key encapsulation mechanism. Suppose I give you a simple equation, 2x plus 5y equals 26. You could try some values and eventually you'll figure out what the x and y are. Quite easy, right? Now imagine many equations at once. Real cryptography uses hundreds or thousands of equations like this. If the equations were perfect, a computer could still solve them. Now add a tiny bit of noise to each equation. Noise means we slightly change the results. Now you see the correct equation, and we'll change that into noisy version here. Just 1 point error makes solving the system much harder. Now multiply that by hundreds of equations, thousands of variables, and random noise everywhere. Suddenly it becomes mathematically impossible with current computers, and maybe even quantum computers, to find the original secret numbers. This is what learning with error means. It basically asks a question. If I give you a huge list of equations that all contain a tiny little random mistakes, can you figure out the secret numbers? The answer: for normal-sized problems, easy. For huge, multidimensional problems, impossible, even for quantum computers. This impossible problem is the security core. Now let's go back to our bad basis vectors. We ended up drawing them here, but let's now sprinkle those little errors into them. We changed their ending points just a bit, and now they don't live in the same lattice anymore. Those errors are so small that they don't matter to us, but they matter very much for the attacker. To solve this lattice problem, we need to use these two vectors to hit a certain point in the original lattice secrets. We'll pick this point here. Its location is pointing into one of the original lattice points. And as we're dealing with mathematics, once again we can add, subtract, and multiply those bad vectors and try to aim this location in here. Now let's try a few. Let's start with 1 positive red followed by 4 negative greens. Another one, 2 positive reds and 6 negative greens. Negative green, positive red, I'm pretty far away. Positive red, 5 negative greens, positive red, and again 5 negative greens, and one more time. And now we got pretty close. Now we keep repeating and repeating different combinations, and finally we try to find the closest vector to the chosen point. It doesn't seem very difficult, you might say. Yes, that is true, as we're only doing it in a two-dimensional plane. But imagine if we can move around in 3-dimensional sphere. It becomes a bit harder. But now get this, we're only using x and y coordinates. In Kyber1024, this is different. Our vectors looks actually like this. We have 4 polynomials, which each has 256 coefficient numbers. So each coordinate is basically a list of 256 numbers. We count them together and we get the number of dimensions we're drawing our vectors to, 2024. You can visualize 2 dimensions. You can visualize and imagine 3 dimensions. 4 dimensions will probably make you scratch your head, as that's pretty hard to visualize or even impossible to imagine. But over 1,000 dimensions? Mind-twisting. So our basic vectors now suddenly became over 1,000 lines moving in unimaginable directions. It's like imagining yourself in a dark room which has 1,024 doors. Behind each door there's another room which also has over 1,000 doors, and so on. You'd be so lost after just a couple rooms. Now we can ask a question. Why 1,024 dimensions is impossible to search? In 2D, you can check the combinations of vectors, maybe a few hundred possibilities. Here we can visualize that. But in 1,024 dimensions, each vector has 1,024 components. Combination space is astronomically large. No geometry can be visualized. No algorithm, including quantum, can search it efficiently. And the noise, those little mistakes we sprinkle in there, makes it even twice as hard. Searching for shortest vector in 2D is easy. In 1,024 dimensions, it becomes this for billions and billions powered to the trillions of combinations. There's no shortcut. Now, how about brute force attack? Just try every possible combination and maybe it'll succeed. Kyber 1024 works with 4 polynomials, each having 256 coefficients. Like I mentioned before, 1024 dimensions. Each coefficient is a number of modulo 3329, and noise values are taken from 5 possibilities, -2, -1, 0, +1, +2. The total number of possibility secret vectors is 5 raised to the power of 1024 equals 2 raised to the power 2077 possible locations. Think that's another big number? Wrong. It's a number where you have 716 digits. I'll show you. Boom. This is how many combinations you have. This is beyond comprehension. The fastest supercomputer in the world is Frontier supercomputer, capable of performing approximately 9.95 quintillion calculations per second. If we harness this computer to try every combination, it will take roughly this many years to find the answer. Now let's divide that by 13.8 billion years, the age of the universe. The answer is 1.29 times 10 power to the 679 times the age of the universe.